Okay, part two to calculus in physics. So I wanted to go over a couple of rules, well, just a couple of ways of doing derivatives and make sure you know. So there are only a few things that we do with derivatives, and for the most part, if you come across something and you're not sure how to do the math for it, look it up on the formula sheet. So the formula sheet includes examples of how to do derivatives and integrals. So this isn't about memorizing how to do math, it's about using math in the way it's intended to solve physics problems. So let me go through a couple examples. So I think last time we were looking at trying to take something, and I like to think of this in terms of graphs. So if I have some position in meters and some time in seconds, and I'll have some function that represents that position time graph. And if I take the slope at any point, or the derivative of that, that'll tell me the velocity at that point. So the nice thing about it is it gives me an instantaneous value, right? So again, if I start with, I don't know, so say my position as a function of time has this function 3t squared plus 2t, right? That I can take the derivative of this to get to a velocity, right? So I'm going to take the derivative with respect to time. So it's going to matter later. Second semester matters more, but first semester almost always you're taking with respect to time. So I take the derivative with respect to time of this thing, this function 3t squared plus 2t. And that'll tell me the velocity. It'll give me an equation for velocity with respect to time. So one of the rules, so last time we went into the power rule, I think it was. So if I had just 3t squared by itself, that I could then take the exponent, multiply this everything by that exponent, and then create a new exponent that's one less. When I have a plus or minus sign here, I just get to do it twice, right? So this is going to be the same. And this is sort of a distributive property, if you like. So this is going to be the same as saying, well, I'm taking the derivative of 3t squared, and I'm adding to that the derivative of 2t. And that I can solve. So each of these, right? So the 3 is a constant. I'm going to pull that out. It becomes really important later when we get to things, especially second semester. So constants, yeah, not affected. So I'm going to pull the 3 out. I'm going to multiply everything by the current exponent and then create a new exponent that's one less. And now I'm going to add this to this derivative, right? So I'll pull the 2 out because it's a constant. I'm going to multiply it by 1, and then I'm going to have t to the 1 minus 1, which is going to be t to the 0. Anything raised to the 0 is 1, so this just turns into 2. So I'm going to have this turn into 6t plus 2, and this is now my equation for what velocity is at any particular time point. I can take a second derivative of this to get to acceleration. Why not? Let's do that, right? So the key things before I get to that each of these is going to have units as well, right? So I need velocity to end up as being meters per second. So each component is going to have a different set of units, and I just need to make it work out, right? So time is always going to be in seconds. So I'm multiplying this by seconds. So if I was to add my units to this, I have 6 times t, and the units for this would be meters per second squared. So notice I multiply it by seconds, I'm left with meters per second. And I'm going to have 2, and I'm going to add here, meters per second will be the units. And this now is going to be my velocity. So units, you just got to make them up so they work out in the end. I could take a second derivative of this to get the acceleration, right? So the rate of change of displacement gives me velocity, and the rate of change of velocity gives me acceleration. So I can end up with a function for velocity, for acceleration as well. All right, so I'm going to take the rate of change of my velocity equation, and this is now going to tell me acceleration at any particular time. So let me think about this. So I can use essentially distribute. So I'm going to say the derivative of 6t plus derivative of 2 equal my acceleration over time. Okay, well I think I know what to do here. So I'm going to pull my 6 out. I'm going to my exponent on t is 1, so I'm going to multiply everything by 1. I'm going to raise t to the power of 1 minus 1, which is going to be 0. So I'm going to have times t to the 0. That's going to become 1. So all of this is just going to turn into the value 6. What happens here? Well, I have t. Well, I don't know. I could think of this as 2 times t to the 0, if you like. I'm going to multiply 0 times all of this, and that's just going to go away, 0, right? So when I have a constant and I take the derivative of that, it becomes 0. So anyway, my equation then becomes 6 is going to be acceleration, and I'll put units on this as meters per second squared. Notice there's no variable in here. I have constant acceleration, right? So my acceleration should be a flat line for this particular one. So it doesn't matter what time is, that I can plug in any value of time, I'm still going to get 6, so constant acceleration. Let me come back to this. So 2, so when we take a derivative of a constant, that ends up being 0. So let me explain one way to think about this. So we'll return to this position graph, right? So let's simplify. So let's look at a position graph that looks like this versus an equation for this, right? So in this one, I'm going to give this a straight line. So what's this going to be? This is going to be my position. So x of t is going to be equal to some slope. I don't know, I'll call it a slope of 3. Sorry, my position times time, constant, and I have some y-intercept, right? So I'm going to add in, I don't know, some 2 there, right? So this is just y equals m plus mx plus b. So notice my y-axis now is position, and I'm calling this x, which is a common variable for position, and this is going to be time. So I get this. So, but the rate of change, right? So my velocity from this is going to be 3. So what's the difference if I change this last component? So what if I change the y-intercept, right? So what's different about it if I have this where x of t is going to equal 3 times t and minus 2, right? So now my y-intercept is down below, right? So my starting point, my 0 time point, I'm starting at minus 2. My 0 time point, I'm starting at plus 2, right? Functionally, as far as velocity is concerned, there's no difference, right? So my velocity comes from the slope of that line. That slope is the same. So these two are going to have the same velocity, even though they have different constant, right? So when you get to derivatives, when I take the derivative of this, I'm finding what's the rate of change, and my constants don't factor into that rate of change. That just tells me where I'm indexed, right? When we get to intervals and we start doing the integrals and we start doing the reverse, then we got something to worry about. But right now, it doesn't matter where the y-axis is. What matters is the rate of change. So these are key things. So I'm hoping that you start getting comfortable with this power rule, and we can generalize the power rule. Well, I'll let you do that. So it's in the homework packet. Let's generalize the power rule, and then we have there's another name for this. I forget. Distributive rule, and then you're dealing with constants and units. We'll do a few other things. So we may have to multiply, take derivatives of functions that are multiplied together, very rarely, and we may divide these things as well. But for right now, and really for most of first semester, what you need to be able to do is to take the derivative, the second derivative, using primarily the power rule, know how to deal with units, know how to deal with constants, and have some understanding of what that's telling you. And again, I like to relate it back to graphs because that makes more sense to me. Hope that helps. Talk to you soon. Bye.